So modeling the entire term structure of interest rate is a sound approach, and modeling the short rate process and then imply the entire the movement of the entire term structure is also a sound approach. Now, between the two sound approaches, there must be a linkage, right? So what HJM wanted to show is that there's a theoretical connection between their approach and the approaches taken from the instantaneous short rate models, which appeared chronologically earlier than their paper. So they want to show that their model is more generic, it's more general, includes those other ones that we have seen earlier as special cases. So let's see how do we demonstrate that. So if you look at this generic approach, let's just take not so generic, let's take a one-factor model for the short rate. Sorry, a one-factor model for the instantaneous forward rate. And if we say this function, instead of a function of time, little t and big T, and whatever omega, which is a state variable there, we just say this is a constant, okay? So if S is a constant, we can actually recover the whole Lie model. Okay, we'll see why that's the case. Now, if S is taking the form of a constant, sigma, times e to the power of minus a big T minus small t, so some function of the time parameter. So a constant times e to the power of a function of time parameter, we can actually recover the whole Y model. So let's see why that is the case. Recall that under the whole Lie model, the zero coupon bond price will have a particular expression like this, which in a way determines the term structure of interest rate. And because that A, we have this log A is taking this particular form here, okay? And there's a closed form solution for options on this process of options on zero coupon bonds, where the zero coupon bond is following this Lie process. Well, I should say the instantaneous short rate is following the Lie process. We have a zero coupon bond expression, and we have closed form solutions for options on those zero coupon bonds. Now, how are we going to recover that? So suppose you take S being a constant, okay? So we see that if S is a sigma, this dv dt is minus sigma, because this volatility here is the volatility of the bond process. And there's a negative correlation between the bond process volatility and the interest rate. So if rate were to go up, the price must go down. So that's why this is a negative sigma here. Now we know this partial derivative of this V with respect to big T is minus sigma. We want to recover this V, which is we want to recover the volatility in this zero coupon bond price process. So how do we do that? Obviously, we're going to integrate. So let's integrate over big T. So if we integrate over big T, we have that V function is minus sigma t plus this alpha term, which is a constant term here. Now this alpha is a function of the little t, but not a function of big T, right? So so we have this and plus this a constant term here that we need to add after the integration. Now, how are we going to determine this alpha? Well, we determine this alpha through boundary conditions. So we know that at maturity, the volatility of the price, zero coupon bond price, must be 0. So V big T must be 0, which means when the little t is big T, this minus alpha T plus, minus sigma big T plus alpha little t, when little t becomes big T, must also be 0 here. And therefore, the only way for that to be 0 is your sigma little t must be the sigma t. So must take this functional form. And then when t becomes big T, they'll cancel out. Okay, so now we know, putting it together, we know that V as a function of little t and big T must take the form of minus sigma bracket times the difference between big T and small t. Okay, so if we substitute S as a parameter, we basically have recovered a price process where it must have the volatility terms that is equal to minus sigma times bracket big T minus small t times P. Okay, the drift term is actually simple because it's a risk neutral process, so everything grows at the rate of R. Now, okay, how do we know this is the price process under the whole Lee model? So we have derived a process from HJM by making S equal to a constant, right? So out of that, we know the HJM process must imply a zero coupon bond process that takes this particular form. So we have to show that this is also the bond process followed by Hou Li. Okay. So what we have here is just a generic process for bonds under risk neutral. Well, under the Hou Li model, we know zero coupon bond must take this particular form. The price of zero coupon bond must take this particular form. And we know the instantaneous interest rate, risk-free rate, must take this particular process as well, right? As we have seen in the earlier lecture. So what is the bond process, with this in mind? Well, if we look at it, then you can use Ito's lemma again. Then by Ito's lemma, the price of the zero coupon bond must be, RT, R times PT, those is the same drift. But the volatility must be dPdR times sigma. Okay, so this is basically based on this functional form and this process, you apply Ito's lemma. Now, what is dPdR? Well, dPdR under this one with this P is basically minus T, big T minus small t times PT. Okay, so then what do you have? So your process here is then R times PT minus sigma T, sigma, you get it here, dP dr gives you this part here. So it becomes sigma T minus TP T function. P is a function of little t and big T dz. So this is exactly what we have seen earlier here. Now we have taken through a different approach by making S a constant. under the HJM model. So which means that when S is a constant under HJM, we have a zero coupon bond process, which is the same as the zero coupon bond process implied from the Holly model. So that shows the equivalence between the two.